Good evening, my YouTube viewers. It is Crystal here. I'm just here because I wanted to do another code review for you. The code review that I did previously on Jax was how to classify images of cats and dogs. And I would highly recommend that if you watched that video to go back and look at the Jupyter notebook, because I have made some changes to the Jupyter notebook, although I didn't make any changes to the video. Now in this particular video, we're going to classify images whether they're pizza or not pizza, and we're going to use the Jax neural network to do that. And then so what we did was I did it in a Jupyter notebook with Kaggle, and it's stored in my Kaggle account. But what I will do is I will save a copy of the link into the description box down below, so that will enable you to actually follow along on the code with me. So the thing that we're going to do is we've got the problem statement, which is to classify images as being pizza or not pizza. And this data set is larger than the previous data set of cats and dogs, because I wanted to see what the accuracy, if the accuracy would improve if I had more data. And then so after we develop our problem statement, which is to classify images whether they're pizza or not pizza, then what we do is we import the libraries that we're going to need in the program. So we're going to import Jax, which is going to create our neural network and perform our numerical computations. We're going to import I said import NumPy, but I don't plan on using NumPy. I'm trying to do everything just in Jax. And one thing that you need to know is while Jax is similar to NumPy, it's not exactly like NumPy. So whenever I translated Jax into NumPy, there were a few little changes, such as the Jax random is different from NumPy random, so that's done differently. And Jax arrays are not mutable, so that's done differently. And then after we imported NumPy, we're going to import random, which enables us to create a random number. But the random number is actually going to be in NumPy, which we haven't used anyway. So that's just an extra library that's not really needed. We're going to import pandas as PD, which is going to create the data frame and read the files. And then we're going to import pale image, which is going to process the image data. We're going to import paths live, and from path live import path, and that's going to work on your file data for the images. We're going to import CV2, which is computer vision. We're going to import OS, which is operating system. We're going to import globe, which deals with global file paths. We're going to import Shuttail, which again deals with file paths. And we're going to import matplotlib.pyplot as PLT. But I don't think we're going to use Shuttail because I used that on something else, but I didn't actually use it in the program. So some of the libraries that I've imported I don't actually need. And then what we're going to do is we're going to use Jax to create our random numbers, and we're going to define it as key. But the thing is the Jax random number is different from the NumPy random number. So I just decided to set up the random number at the beginning of the program. We're going to use the OS library to go in and retrieve all of the files, and we're going to be looking at the JPG files, and they're either going to be not pizza or pizza. So we retrieved all these files. Okay. And then what we're going to do is we're going to view the images with the image function. And you can see that when we view the image with the image function, we're viewing two images, and one image is a piece of pizza, and the second image looks like Doritos, so it's not pizza. So now what we're going to do is we're going to load and process the images, and we're going to define a function called load and preprocess images. So image data and image labels are a blank array. And then for file name in OS list dir folder path. So you're going to get all of the file names. If the file name ends with JPG or the file name ends with PNG, then you're going to do some work on that file. So img equals cv2.resize, img, comma, img dot, comma, at 128, 128, img equals img.astype float 32 over 255. So if the number of, if the shape of the image is 128 by 128, then 255 is going to be the binary equivalent of 128. So what it's going to do, is it's going to make all the values in that particular image be range from 0 to 128. And that's why it does that. And you could just as easily say img.max, and that would be just as easy as to say 255, but they're working on the assumption that every value is going to be between 0 and 1. Now you're going to flatten it. img flat equals img.flatten. And now you're going to append the flattened image to the data. So image data.append img flat. And now you're going to append the label. So img labels.append label. And then you're going to, let's see where we've got the label. Okay, the label will be later on. And then it's going to return np.array image data, np.array image labels, but really it should have been JNP and not NP. So that was a mistake that I made. So whenever I finish this code review, I'm going to have to go back and change that. That's one of the reasons why I like doing code reviews, because if I make a mistake, then I can pick it up in the code review. So now we set up the path to the folders. So pizza folder is a path and not pizza folder is a path. And now we load and process the pizza images, the pizza data and labels, and we use the load and preprocess function, being pizza folder and label equals 1. And then so we print the shape of pizza data shape and pizza label shape. And then we preprocess the not pizzas. So not pizza data, not pizza labels equals load and preprocess images. Not pizza folder is label equals 0. Print not pizza data dot shape, not pizza labels dot shape. And now what we're going to do is we're going to destack the pizza data and the not pizza data, and we're going to concatenate the pizza labels and the not pizza labels. And now what we're going to do is we're going to shuffle the data. So indices equals jnp dot arrange x shape 0. Indices equals jx dot random dot permutation key. Indices axis equals 0. Independent equals false. So x equals x indices and y equals y indices. And then so we just print y to see what y is. And now we reshape y because the program won't work if you don't reshape it. And now what we do is we take the data and we convert it into training and testing sets. So the split ratio is 0.8 and the split index equals int split ratio times x shape 0. And then we split our training data and our testing data, and then we print the shape of that, and then we print y-test just to make sure y-test is correct. So we've got y-test here. Now we define our neural network. So we set up our input size as x.shape1, hidden size is 128, output size is 1, learning rate is 0.01, epochs is 1000. So we set up our initialized weights and biases. So your weights and biases are going to be formed by a matrix that has all zeros, and weights input hidden equals Jack's random normal key, shape equals input size hidden size, biases hidden equals JNP dot 0 1 hidden size, weights hidden output equals Jack's dot random dot normal key, shape equals hidden size output size, biases output equals JNP dot zeros 1 output size. So now what we do is we set up our sigmoid function, which returns 1 over 1 plus jnp dot exponent negative x, and then we set up our sigmoid derivative and return x times 1 minus x. So now what we do is we train the neural network, so for epoch and range of epochs. So we set up our forward paths, hidden input equals jnp dot dot, x train weights input hidden plus biases hidden. Hidden output equals sigmoid hidden input. Output input equals jnp dot dot, hidden output, weights hidden output plus biases output. Predicted output equals sigmoid output input. And then we're going to compute the loss. Loss equals y train minus predicted output. Then we're going to set up our backpropagation. Output error equals loss times sigmoid derivative, predicted output, hidden layer error equals output error dot dot weights hidden output dot t, that's transform, times sigmoid derivative hidden output. Now we update the weights and biases. Weights hidden output equals weights hidden output plus hidden output dot t dot dot, output error times learning rate. Biases output equals biases output plus jnp dot sum, output error axis equals 0, keep dims equals true, times learning rate. Hidden input hidden weights input hidden equals weights input hidden plus x train dot t dot hidden layer error times learning rate. Biases hidden equals biases hidden plus jnp dot sum, hidden layer error, axis equals 0, keep dims equals true, times learning rate. So now what we're going to do is we're going to test the model. So hidden input test equals jnp dot dot, x test weights input hidden plus biases hidden, hidden output test equals sigmoid hidden input test. output input test equals JNP dot dot hidden output test weights hidden output by plus biases output. Predicted output test equals sigmoid output input test. And then you convert predicted probabilities to binary predictions. Predictions equals predicted output test is greater than 0